Okay, this is the 14.2 video. We are moving on from double integrals over rectangles to double integrals over general regions. So they're giving you a little bit of an introduction to this section here in this paragraph. This is page 768. And it's talking about how now, just at the bottom here, the limits of integration are going to sometimes involve variables on the inner limits of integration as opposed to just constants like they were before. So last time when they were constants, we were able to just swap them around very easily and it was no problem, but now that they're not constants, you can still switch the order, but you can't just swap them. They change when you switch the order. So that's what we're going to look at today in this video. So on page 769, they're talking here about volumes and that double integrals of functions of two variables represent volumes. And so you have some sort of curve on the top, curve on the bottom kind of a thing. Typically the ones we're looking at, you have the XY plane on the bottom and then some surface on the top. But before, the region in the XY plane that was on the bottom was a rectangle. And now the region that's in the XY plane on the bottom, something like this maybe, is not a rectangle anymore. And so it makes it a little more complicated to integrate it. And so if you were thinking about this, like for instance, let's look at this box. If you were thinking about approximating the integral, which we're not going to do, but just to give you an idea of how this would work, you would find for volume, you could find the area of the bottom, which would be base times height, and then multiply times the height to get the volume, because base times height, well, sorry, let me do that, length times width. Okay, so length times width would be the area of the base, and then times height would be the volume. So length times width times height would be volume. And so it's the same idea for when you're doing it for real, not using rectangles to approximate it. You would find the area of the base and then you would basically multiply it times the height. But it's a little more complicated than that when it's not a box. And so that's kind of what's going on here in this first thing that they're talking about. This part would represent the area of the base, and since the base is not a rectangle anymore, it's a little harder to find it, so you can use an integral, a single integral, to find it. And you would be integrating between two curves or two functions. And so then once you do that, then for the height part, now you add the second integral, and that's going to give it that third dimension to it. And so you have y being between two functions of x, and then x being between two constants. So this is one way to do the volume. And the other way to do the volume is on the top of the next page, page 770, and that would be now if x is between two functions of y, and then y is between two numbers. And so notice the outer bounds, the outer limits of integration, they are numbers. And then the inner ones, those can be variables. You can never, 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 never have variables out here on the outer one. The outer one has to be numbers, but the inner one can be variables. So I sort of lied to you, but I sort of didn't. I just didn't explain myself very well in the previous video when I was telling you about Fubini's theorem. Fubini's theorem, here they have it again in this section and you can still use it, but what I meant in the last video by you can't use Fubini's theorem unless all four of the numbers were constants, I meant that in using Fubini's theorem there, we were just swapping them. Like for instance, let me just show you what I'm talking about. Like if you had 0, 1, 2, 3 or something like this, and you had some function, let's say this was x and this was y, then according to Fubini's theorem, you can integrate in either order if the function is continuous. And so you could have literally just switched them like this. And that's totally fine because that's the same thing if all four of these, 1, 2, 3, 4, if all four of these are numbers. You can literally just switch them and you don't have to change anything. Now, you can still use Fubini's theorem in that you can still integrate in either order, but you cannot just swap them. So it's a lot more work now when we don't have rectangles than it was before to apply Fubini's theorem. So Fubini's theorem can still be applied, but the literally swapping them and not changing anything doesn't hold anymore. Okay, so that's the part of it that I was saying doesn't hold anymore, but Fubini's theorem does still apply in a different situation, a different method, I guess. I don't know what's the best word there. Okay, so this is page 770. And again, the function has to be continuous over your region. And so you have the two situations here. Either the y can be between two functions of x, and then the x between numbers, or the x can be between two functions of y, and the y can be between two numbers. So you can do either y first and then x, or x first and then y, but when you swap them, they don't stay the same. Okay, so they change, they're different. And so that's what we're going to be looking at in this section. And so down here at the bottom of page 771, it reminds you of what we were talking about in 14.1, in that sometimes one way is easier than the other. And so sometimes one way is going to be better, even though both ways would work, if that makes sense. Both ways would work, but one way sometimes is much better. All right, so they have here, and I'm not going to read this to you, obviously, because I never read anything to you, but page 772, I'm going to show you with an example, because I think that makes more sense than just reading it here, because reading it here doesn't even make a whole lot of sense to me, and I know how to do this. So page 770, if you want to go back and read this later, after we've looked at some examples, it'll make a lot more sense maybe then. But it starts here, finding limits of integration using vertical cross sections or horizontal cross sections. And so I have a kind of a way that I think makes more sense that I'll show you than what they're talking about here, but it's the same thing. So sometimes seeing it presented differently makes more sense or helps you, and so this way you'll have two different ways to think about it, my way and the book's way, and whichever way makes more sense to you would be great for you to think about, because they're both okay. Then page 773, just some properties of integrals, and this is just kind of showing you that the same kind of things that you can do with single integrals here you can do with double integrals, constant multiples, sum and differences, etc. So nothing too exciting there. Let's look at some examples though. Be careful to read the directions here, because they're all asking you to do different things. It's always changing on what they're asking you to do. So here in 1 through 8, all they want you to do, what in the world is wrong with my book? Who knows? Okay. All they want you to do is sketch the regions. So you're just drawing the pictures here. So just, if you can't graph, you're going to have serious issues for a while in these sections, because you got to draw these things before you can integrate them. So practice your graphing lots and lots. Okay. So these are just the formulas from the section. Again, just a reminder, the numbers have to be on the outside, the bounds. The functions have to be on the inside. If you do it backwards, it's bad, very bad. Where are my papers? Okay, hold on. Okay, here we go. Example number, first example, but it's number 2. My screen is so dirty, I can't even tell if this is focusing or not. I need to wash my screen. Okay, so here's the example. And you have that the x is between -1 and 2. And notice the y is between two functions of x. So you have y equals x minus 1, which is this line with y-intercept -1, slope +1. And then you have y equals x squared, which is the parabola. And so notice these cut them off on the left and the right. This cuts off the left side, and this cuts off the right side. They are vertical lines. So you have this vertical line at x equals -1, this vertical line at x equals 2. And it cuts them off on the sides, and so that would be my region. And you want to shade your region. So whenever it asks you to sketch the region, you have to draw the edges, what makes up the region, but then you also have to shade it. So if you do not shade it, you will lose points. You have to shade in addition to sketching the region. All right, number 6. Try this one by yourself. Number 6, you have x between 1 and e squared, y between 0 and ln of x. So try that by yourself. Pause the video and then come back and check it. Okay, so this is what it should look like. Make sure you shaded, and you always want to label important points. So you've got an x-intercept at 1, and then here where is e squared, that corresponds to a y value of 2, because this is y equals ln of x. If x is e squared, then the ln and the e cancel, just leave you with 2. All right, so that's kind of like warm-up exercises, getting ready for the real stuff. So now let's look at, these are still more warm-up exercises, but we'll look at this next group. It is page 775. Can you hear that wind? A storm is coming, I think. I have a lot of trees in my backyard, and the wind is blowing like crazy. If it starts raining and my skylights start leaking, I'm going to have to stop this video and do it in 2 parts. So just pray it doesn't start raining. Okay, 9 to 18. Write an iterated integral. Remember, that's just the double integral version of a definite integral, so it just has to have bounds on it. over the described region R using A, vertical cross sections, or B, horizontal cross sections. So we are going to look, what are we going to look at first? Hold on. Number 12. We're going to look first at number 12. They already drew the picture for us. So here's the idea. You have some sort of three-dimensional surface above this, or below this if it's negative. I don't know. And then this is the region in the xy plane that you're integrating over. So it's like if let's say the function is positive, so it's above the xy plane. Then above it is the surface, and this is what's on the bottom, on the floor, kind of, if you want to think about it like that. So this is not the actual surface itself. This is like the shadow of the surface, if you want to think about the sun being directly over the surface and it's just shining down this little section. Okay, I do these arrows for my cross sections. So if my cross section is vertical, my arrow would be going from the bottom of the region to the top of the region. So I think this is easier because I'm a visual person and you can visually see or visually look at this to answer the questions, what's on the bottom of the arrow and what's on the top of the arrow. All right, so you can see on the bottom of the arrow, well, first of all, if it's vertical, ask yourself which axis goes that way. Which axis goes up and down? That would be the y-axis. So that's the one that's going to be first in terms of what you're going to integrate with respect to first. So it's inside. That's the one that's inside because you're integrating first. And so that would be y because y moves up and down. So that's the one that's going to have the functions, right? It's going to be the one that has the functions because that's inside. So on the bottom is the line y equals 1. And on the top is the curve y equals e to the x. So your y is between 1 and e to the x. Then the other one has to be between numbers. So the x has to be between numbers. So you can see that's between 0 and 2. So my x is between 0 and 2. So notice I'm doing y first and then x. So the one that you're doing first goes on the inside because you work from the inside out. So inside is y. Here's my bounds on the y. Smaller one on the bottom, bigger one on the top. And then x is on the outside and it's between 0 and 2. Okay, so that's for vertical. All right, horizontal, you're going to do x first and then y. So here's the picture. So notice for horizontal, my arrow goes horizontally. And the x-axis is the one that goes that way. So you know you're doing x between functions and you're integrating with respect to x first. So you would ask yourself, what's on the left of my arrow and what's on the right of my arrow? But remember, if it's x's, x's have to be between functions of y. And this is not a function of y. This is a function of x. You cannot use it. You can't have x's being between x's. That doesn't make sense. X's have to be between functions of y's. So that came from y was equal to e to the x. So if y equals e to the x, you need to solve it for x because you want to know what x equals. So you take the ln of both sides. Ln and e cancel out. So this is the same curve, but it's written where x is a function of y. So it graphically is the same thing. It just now is x equals a function of y. So on the left side, you have that curve. So that would go here, ln of y. On the right side, you have 2, so that would go here. And then your y is going to be between numbers. So at the bottom is 1, at the top is e squared. So y is between 1 and e squared. And then again, you're doing x first, so it goes on the inside. So these are my x's, and these are my y's. Okay, so see how those are different? So according to Fubini's theorem, in terms of getting the same answer, it wouldn't matter which one of these I did. But notice when I went from this to this and I swapped it from y first to x first, I didn't do like what I was doing with Fubini's theorem in 14.1 and just flip them. That would have been totally wrong. What I'm talking about is like, don't write this down. Don't write this down. This is very bad. Don't write this down. You would not have just done this. Like see how here, and then you just swap them. That's wrong. Very bad. Because see how I have a function on the outside? That's not okay. So don't do that. That's bad, bad, bad. Don't do it. So this is, it's different than Fubini's theorem from before. Okay, so that's what I was talking about last class, or last video, when I was saying that Fubini's theorem only holds when they're all four constants. What I meant by that was that the swapping. You can't just swap the order arbitrarily without changing anything, unless they're all numbers. Okay, so let's look at another one of these where they don't give us the picture. We're going to look at number 16. So number 16, you have y equals 0, which is the x-axis, x equals 0, which is the y-axis, y equals 1, and y equals ln of x. So you're going to graph all three of those. So you've got here the y-axis, which is x equals 0, here the x-axis, which is y equals 0, here's the line y equals 1, and then here's the graph, or the curve, y equals ln of x. So that's my region. Okay. Now to see what this number was, where these graphs intersect, I wanted to see where the line y equals 1 and the curve y equals ln of x intersected. So to see where that was, I just set them equal to each other. So ln of x equals 1, take the e of both sides, e and ln cancel each other out, so x is e, and that's how I got that e. Because you need to know where they intersect. You need to find the points of intersection because you're going to need them for your bounds. Okay, vertical cross sections, that's with the arrow. I didn't keep drawing the arrows in the picture because I didn't want to have to keep drawing the pictures twice, so just drew the arrows out to the side. That's when the arrow goes this way. But notice here's a problem. If you're here in this square part, see how on the bottom is the x-axis and on the top is y equals 1? But if you move over here to this curved part, this part number 2, see how now it's something different on the bottom? The curve is on the bottom. So when that happens, where you have in this section one thing on the bottom and this section another thing on the bottom, or on the top or the left and the right, if it changes, if it ever changes, then you're going to need 2 integrals. So this is going to need 2 integrals. So I have to split it in half, not really in half, but I have to split it into 2 parts where the pink line is. And I'm calling that section 1 and section 2. So in section 1, and if I'm going this way, normally it would be the y's being between functions, but this is a square, which is a special case of a rectangle, which is where all 4 of them are numbers. So this one, they're all 4 going to be numbers. So y is between 0 and 1, x is between 0 and 1. But when I move into section 2, my arrow is going up and down. On the bottom is the curve. That would be the ln of x. On the top is the line y equals 1. So I've got y being between ln of x and 1. And then in that section, that starts here, that's between 1 and e for my x's. Okay, so 2 separate integrals. This one, again, because it was over a rectangle, they're all constants. This one, it wasn't a rectangle, so you see how you have functions on the inner one. All right, but when you do it with the horizontal cross sections, that one's with x first and then y, and the arrow goes horizontally. Now you only need 1 integral. And so your curve was y as a function of x, but now you need it as x as a function of y. So you, again, take the e of both sides. No, last time I took the ln of both sides. This time I'm taking the e of both sides. Similar but different. And so x is e to the y. So again, same curve, but written as x equals a function of y instead of y equals a function of x. Okay, so if I'm going horizontally with x first, x is the one that's between functions. So up here on the left, I have 0. On the right, I have the curve. So that would be this. What is all over? I have pink and blue and who knows what all over my fingers. What in the world? Who knows? My daughter's friend was over here today, and she was trying to glue something, and she got super glue all over her fingers, and she was just freaking out about it. 'Cause it was tearing her skin, apparently, her fingers were stuck together when she tried to pull them apart. She was like, oh, it hurts. It was hilarious. I totally should have gotten that on video. That would have been highly entertaining. But nope, my daughter's not here now because they left to go somewhere, so you'll have to wait till another day to meet my daughter. So sorry. All right, anyway, so here's this one. Again, a single integral. Well, it doesn't need 2 separate integrals. It's still a double integral, but it doesn't need 2 separate ones like this. It's kind of confusing, sorry. Anyway, so this would be x first and then y. All right, so I'm going to have you try this one by yourself. Same thing, number 18. You are first drawing the picture, then you're doing it part A vertically and part B horizontally. So I'm going to have you try it by yourself. So pause the video, try number 18 by yourself, and then come back and see if this is making sense. All right, I hope you actually are trying these things. I have no way to know whether you're trying these things, except you're probably going to do better on the test if you are, and you're going to do worse on the test if you aren't. So I guess it's really your call. I'd love for you to do better on the test, though, because it makes my grading easier if you do well. And it makes me look good. And it makes you happy, so it's like win-win all the way around. So I hope you're pausing the videos and trying these. That'd be great. Okay, so here's your picture. You have the parabola and the line, and then you want to see where they intersect each other. So sometimes you can just tell from looking, and sometimes you can't. If you can tell from looking, you don't have to show this work. I just show this work for the people who can't tell from looking. So you want to see where the 2 graphs intersect each other. So they're both solved for y. So you set them equal to each other. And when you set them equal to each other, you're just solving for in this case x. All right, so you have to get it equal to 0, so you can use the zero product property when you factor. And then you get x equals 2 and x equals -1. So here's the x equals 2. Here's the x equals -1. That's where they intersect each other. And I'm going to need those for my bounds. That's why I did that. All right, so hopefully you already did this. Part A was easy. I should have warned you. Part B was tricky. I didn't warn you. So if you didn't get part B right, don't feel bad. All right, so here's hopefully what you did for the vertical. You have y first and then x. So y has got the parabola on the bottom and the line on the top. And then the x is between the -1 and 2. All right, for the horizontal, you have to change them. They are currently y equals a function of x, and you need them as x is a function of y. So you've got to solve them both for x. So notice here when you solve it for x, you need the plus or minus. And then here when you solve it for x, it's just another line. Or another equation for a line. Of course, it's still a line. All right, but notice the picture. I don't know if you noticed this when you tried it by yourself. I'm sorry, I should have warned you. This region needs 2 integrals because there's different stuff on the left depending on where you are. So if you cut it off right here, and I drew it over here so the axes wouldn't be in the way. So this is with the axes, this is without it. So if you cut it off right here, see how right here you've got one thing on the left and right here you've got something else on the left? All right, so you need to figure out what you have. So in section 1, that's that bottom part. On the left I have the parabola and on the right I have the parabola. But one of them would be where x is negative and one of them would be where x is positive. So I've got the negative version here and the positive version here. And then to see where that happens, where that cuts off, that would be this endpoint here where x was -1. So if x is -1, you can plug it into either one. You can plug it into y equals x squared, or you can plug it into y equals x plus 2. It's the same. It's going to give you 1. So the y would be between 0 and 1. And then in section 2, you have the line on the left and the parabola on the right. So here's the line, here's the parabola. Again, as functions of y, not functions of x. And then the y would be from 1 to 4. The back of the book, when I was checking my answer, had 1 to 3. I'm 98% sure it's not 1 to 3. But if for some reason you think it's 1 to 3, let me know where you think they got the 3 from. I think it's just a typo, but I could be wrong. But I'm pretty sure it's 4. Okay, so 2 integrals, 2 double integrals here. This would be the one for section 1, and this would be the one for section 2. So that was a tricky one. If you did get that one right, way to go. That's very impressive because that one was kind of tricky. If you didn't get that right, again, don't feel bad because those are some crazy ones and I forgot to warn you about it. All right, moving on. 19 to 24, sketch the region and evaluate the integral. So here they have already set it up for you. So if they've already set it up for you, you don't really need to sketch the region. They're just letting you practice with that. But if this were like on a test or something, if it was already set up for you, there would be no need to sketch the region. The only time you need to sketch the region is if it's something like this, where it's not even set up for you at all. All right, so here we go. Here's what I have. So you want to pair them up. Inside is this and inside is this, so they go together. So that's the bounds on the y. Outside here, outside is here, so those go together. That would be the x. So here's my region. Again, shade. You've got to shade. All right, then you're going to integrate. So you're integrating the y with respect to y. So it gets you this. You're plugging in for y. So you have sine squared. You cannot integrate sine squared. If you write 1/3 sine cubed, that just makes me want to smack you. I wouldn't actually smack you because I'd probably lose my job. But it just makes me want to smack you, just so you know. So don't put 1/3 sine cubed. That's very, very bad. It would be this identity that you have to use. I'm just kidding. It doesn't really, in case that hurts your feelings, I'm totally joking. I don't really want to smack you. But it does make me want to just take off like all of the points and not give you any partial credit. That is true. The smacking part, I was kidding. Here is the trig identity that you want to use. And then you can integrate that. And that is okay to integrate. And so it will be this when you integrate it. Then you would plug in your pi and your 0. And a bunch of those are 0. So it just leaves you with pi over 4. So these, again, what you're finding is volume. These represent volume. And it is possible to get negative answers because just like with area, If the function was above the x-axis, it was positive, but if it was below the x-axis, it was negative. Same kind of idea here. If the surface is above the xy plane, it's positive. If the surface is below the xy plane, it's negative. So it's okay if you get a negative answer. Don't let that freak you out. All right, try this one by yourself. Same group of problems. This is still the 19 and 24. We're going to do 24. You're going to pause the video, try 24 by yourself, then check back with me and see if you got it right. Ready, go. All right, here we go. See if you got this right. The current way that it's set up is with y first. So your graph should look like this. Notice it don't shade in here in this little section between 0 and 1. Don't shade in there because it's not there. See, the x is between 1 and 4, not 0 and 4. So make sure you did not shade in there. All right, then you're going to integrate with respect to x. Notice that the square root of x in the denominator here is like a constant. So when you have a constant, you do the reciprocal of that. So the reciprocal of that ends up being the square root of x. Okay, and then that simplifies down to there's your Cal A integral. So you can check your work so far. And then the next page, you should have ended up with 7 times e minus 1 or 7e minus 7, whichever, doesn't matter. But hopefully you got that one right. Okay, let's move on. Next group of problems, 25 to 28, integrate over the given region. So this is now the real deal. You are graphing it yourself, you're setting it up yourself, you're integrating it yourself. So warm-up time is over. This is the full-on problem. Ready, go. F of x equals x squared. What number is this? 26, sorry. You have the triangular region between these 3 points. If you can tell what the equation for that line is, like you just recognize it or you can figure it out, you totally do not have to show this work. But this is just for people who can't tell what that is. So if you can't tell what that is, you can find the slope, and then here's your y-intercept is 1, your slope is -1, so it's this equation. If you could tell that already, then you don't have to do this work, but that's just for the benefit of people who couldn't tell already. All right, you can do this vertically or horizontally. I think, hold on. No, I set it up both ways. I didn't actually work it out both ways, but if you can set it up either way, and it's equal amounts of work either way, vertically is better because on vertically, it gives you y as a function of x, which is much more natural. X as a function of y is not natural. It's not what you're used to doing, so you're more likely to make mistakes. So if you have the choice, vertical should be your first choice, just because, again, it gives you y as a function of x, which is something you're more comfortable with. Okay, so the y's at the bottom would be 0. At the top would be the line. The x's are between 0 and 1. So you set it up with the y's on the inside if you're doing this vertically. So you have the functions in here. Then you're integrating with respect to y. Simplifying. This one, there's a little shortcut formula. This is 1 minus x cubed. Hold on, let me put my pencil in my book so I don't lose my place. Here, was it minus or plus? Where are you? It was minus. So this is in this little cardstocky paper at the front of your book. Here's that shortcut formula for it. If you want to use that, it's much, much faster. If you already know that. That's what I use, so that's why I didn't show a whole lot of work there. So there you go. Distribute the 1/3. Put all your like terms together, and this would be your Cal A integral. This one, fractions, but it's easy to integrate. So integrating, plugging in, it's a polynomial, so you're going to get 0. And it gives you 1/6. All right, you can also, though, set it up horizontally. I didn't actually work it out because the work is similar, but if you set it up horizontally, notice your line was y equals a function of x. You got to get it as x equals a function of y. And then your x's, going back up to your picture, your x's have 0 on the left, the line on the right, and then the y's are between 0 and 1. So setting it up, it would look like this. This is ... for, there's all the work I was too lazy to show, equals the same thing. Okay, so that one, the level of work is the same, but it feels less weird maybe to have y as a function of x than it does to have x as a function of y. All right, the next group of problems. This is a long section. I guess you could tell when you looked at the video and saw how long it was, but anyway, here's the directions. 29 to 32 gives an integral over a region in a Cartesian coordinate plane. Sketch the region and evaluate the integral. So they've already set it up for you. So again, under normal circumstances, you wouldn't need to sketch it. They're just letting you practice with this. We are going to do number 30. So this is the problem. So number 30, notice you have the ST plane. So instead of XY, it's ST. So they've already got it for you. the t's are between this and the s's are between this, and so this is going vertically because the t is like the y and the s is like the x. They're alphabetical. Okay, so the whole thing, here's the work for that. The t equals the square root of 1 minus s squared. That, if you square both sides, becomes this, and then if you add the s to both sides, becomes this, which is just the unit circle. So notice that's the unit circle, but because the t's are between 0 and the unit circle, that would only be the top half. But then because s is between 0 and 1, that's only the top right. So it's just the part in the first quadrant. So shading, you're only shading the first quadrant. Okay, so now you integrate. Hopefully you're getting more comfortable with integrating now that this is the second section of integrating. The new stuff here is setting it up. So integrating, you don't have to distribute that 4 there. You can factor that 4 out. But I just distributed it. I didn't factor it out. I don't know why. And so that ends up being 8/3. All right, next group, 34 to 46. Sketch the region, write an equivalent double integral with the order of integration reversed. So they did not ask you to integrate these, so don't integrate them unless you just want practice, but you don't have to. So if you want to practice with it, you can integrate it. If you don't want to practice with it, you don't. Notice the thing you're integrating is just a 1 the first time, so they are really easy to integrate. 36. I have this as my original problem. So because the y is first, that's vertically. So I have y between these. So this one is a parabola. Shifted up one and opening down. This one is a line. So that would be this. Shade again, always shade. But now because I'm going to switch it and I need x to be first, I need x's as functions of y. So here's the line as a function of x. Switch it to be as a function of y. Here's the parabola as a function of x. Switch it to be a function of y. Notice here when you solve for the x and you take the square root to both sides, you would need the plus or minus. But if you look at this region, see how the x is already always positive? So if the x is already positive, you don't need the plus or minus. It's just the plus case. All right, so going horizontally now, if you're going horizontally, on the left is the line and on the right is the parabola. And then your y is between 0 and 1. So setting it up, not integrating it, would give you this. All right, I'm going to have you try one by yourself. Hold on. Let me see what number it is. 38. So 38 is here. Try this one by yourself, same thing. Sketch it, switch the order, set up the new integral. Don't integrate unless you just want to practice with integrals. So pause the video, try 38 by yourself, and then come back and check your answer. All right, so here's hopefully what you did. You have this picture. And that was when it was going horizontally because the x was first. Now you need to just switch it to vertically. So you've got to change this from being a function of y to now being a function of x. So you took the ln of both sides, and you got y equals ln of x. Now going vertically, you should have had this. So check outside 1, 2, inside 0, ln of x, y first, then x. All right, hopefully you're feeling okay about this section. I did lots and lots of problems so that you'd have lots and lots of examples to look at. I may not go over all of them. I'm just going to show you a few of them, and I'm going to post these notes on Angel later. So if you want to try these by yourself, I just did some extra ones so you'd have some more to look at in case it was confusing. So, but for the sake of keeping this video small enough that I can actually get it to upload, I'm not going to go through all these. But here's 42. You can pause the video and look at that if you want to. Just another example. And then here's 50. Again, just so you have another example. You can pause the video and look at that if you want to. Those are pretty straightforward, nothing weird going on with either one of those. Okay, just more examples. And then also 54 is another one. Okay, so these were I was just trying to do lots of examples so you have plenty to look at. So 54, same kind of thing. Actually, that's a different set of directions. They want you to actually, oh, so is 50. Sorry, hold on. I didn't read the directions. Different set of directions. 47 to 56, sketch the region, reverse the order, and now evaluate it. So 50, here's where I sketch the region. Here's where I switch the order, and then they did want you to actually integrate it. So that was the answer there. So you're doing more stuff here. And then same thing with 54, sketch the region, switch the order, actually integrate it. Okay, very similar to the other problems, you just have to keep going because you have to actually integrate. But now let's look at one that's different. So turn the page. 776, number 60. find the volume of the solid in the first octant. So that's the three-dimensional version, of course, like the first quadrant. It's where x is positive, y is positive, and z is positive. Bounded by the coordinate plane, so that's the xy plane, the yz plane, the xz plane. The cylinder, x squared plus y squared equals 4. That's a cylinder that's opening around the positive z and negative z axis. And then the plane, z plus y equals 3. All right, so here's what's going on. I didn't draw the plane because my picture would have gotten way too crazy, but here's the cylinder. Okay, but you want to stay in the first octant. So see, I've only shaded the first octant part of that. So that's what's on like the floor, right, at the bottom on the floor. So I drew it here in the two-dimensional xy plane. This is three-dimensionally the cylinder, but you want to take the section in the xy plane, which would be the floor, and that's this. And then the plane here, that's like the top, right? You have on these three-dimensional things that you're finding the volume of, you have the thing that's on the top if it's positive, and then you've got the thing that's on the bottom, which is the whatever's in the xy plane. So this is the part that's forming the top. So you need to solve it for z, and if you solve it for z, then this is that function that you're integrating, the f of xy. So this is the f of xy, this is the region that I'm integrating over, and so now I can set it up. So here's my r. I need to solve it to get, well, here you can do it either way. Again, whenever you can do it either way, vertically is the better way to go because it makes more sense to have y as a function of x. But it would have worked the other way too. So either way, I did y as a function of x. So this, solve it for y, put the plus or minus, but you can see y is always positive, so you just need the plus case. So the y's got 0 on the bottom, the circle on the top, and then the x is between 0 and 2. So you put that, here's my function again that comes from this plane. Put that in there, and then integrate with respect to y. And now here's the fun part. Just because I know you missed this from Cal B, I wanted to make sure to pick one, trig substitution. Didn't you miss trig substitutions? This will make an excellent kind of bonus type question because it forces you to remember Cal B. So I did that out to the side here. Trig substitution just for this piece. So I just focused just on this piece. Came over here to the side to do it. 8.3 is where this is if you forgot. So integrating this, you make this trig substitution, find the dx, plug it all in, simplify, simplify, simplify down to this. That is not 1/3 cosine cubed. That will make me take off all of the points, and I'll be upset with you. So don't do that. You have to do the trig identity, so you can integrate it, and then you get this, which another trig identity, that's 2 sine cosine. And the 2's and 1/2's cancel. Now figure out what all that stuff is. So you make your little triangle. Here's sine, which is opposite over hypotenuse. Find the missing side. Figure out what your pieces are. Plug all your pieces in, and you get this. So all of this was for just this integral piece. So I put that back over here. So this piece had the 3 in front of it. So that one piece was all this stuff that's from the box. And then integrating the 2 is 2x. Integrating this. And then simplifying, plugging in the 2 and 0. And it works down to this. So that was throwback to Cal B because I know you missed that trig substitution stuff. All right, that is all from this section. If you have any questions, email me. Make sure to practice with your graphing and your integrating because there's a whole lot more where this came from.